morning, everyone. All right, before I start, just a reminder that starting Monday, the classes will be face-to-face and we meet in the CLO 151. Okay, I will put this announcement on Brightspace as well. Second, before I forget that your first exam is next Friday, a week from today, February 4th. The review for the exam is already on Brightspace. So on Brightspace, you will have a review for the exam, and it will be barely what we're doing. Nothing really different than that, just more practice problem. Okay, and the exam, of course, will be face-to-face. So be ready for that next week. All right, so these are small announcements. Okay, now back to you. Any questions about the homework? Please get going. Okay, any problems, you guys? Any questions about the homework I assigned for today? Can we solve number 15? 15, what is it number 15 about? Okay, we can look at that. And here we have a region. And we have the graph, that's the line, y equal 4 minus x. And y equal to 2. And this is the region. And we're rotating around the x-axis. Okay. And the question is, find the volume. All right, so let's do that. Now we have two ways, basically, of doing the problem. We can pick the one we want. We have the washer and we have the shell. Okay, all right, which one would you like to use? And does it matter in this particular problem? Anybody had any preference? Okay, speak up, guys. All right, we can do both, just as a practice. So we're gonna do first the washers. Right. So in this case, this is my axis of rotation. I'm going to take slices. This is my xi. Perpendicular to the axis of rotation. So I'm going to take those vertical slices. Okay. And I rotate them. So I rotate the first one. And I rotate the second one. So we're going to get this washer right there. Right. So now the question is, you have to find inner, outer, the intersection, definitely. And then we set up the problem. Okay, before we do that, we know that we have to find the interval on the x-axis to be able to, the interval that we need to divide. To do that, we need this point. All right, what is this point? Right here, y is 2, so we want the x. We have 4 minus x equal to 2. It means that x is equal to 2. So this point right here is 2. So that's really the interval we're interested in. Now, washer, we need inner, outer, and the height. So the inner, the outer, and the height. Now, the height of my washer is this little bit, delta x. The inner is from the axis of rotation to the, basically in this problem, the bottom term. So it's from here to here. That's my inner, which is very easy in this case, which is equal to 2. Now my outer is from, that's my axis of rotation, to the farthest curve. It means to this one. Now x is my variable. So this is my xi. Basically, I need the distance from here to here. This vertical distance. This is given by the y. So this is right here. This is the 4 minus the xi. So my outer is 4 minus xi. And finally, my height is the delta x. Now we're actually done. Volume of the washer. Almost equal to pi times the outer radius square minus the inner square times the height delta x. And the total volume is the integral. Now, which interval I need to split is the interval from 0 to 2. Minus 4 dx. Okay, and now to find the antiderivative, basically the only way we can do it is to expand this term, which gives me 16 minus 8x plus x squared minus 4. Combine like term and then integrate. 16 minus 4, it's a 12 minus 8x plus x squared dx. And the last step is find antiderivative, which is easy in this case. 8, antiderivative of x squared is a half x squared, of x, plus antiderivative of that is 1/3 x cubed. The whole thing between 0 and 2. Okay. Any question? Now, let's say I want to do it using the shell, the shell method. Why not? I think this is easy either way. So let's do it using the shell method just to practice both. So it's the same region. This is my line, y equal to 2. And this is y equal 4 minus x. Okay. And we're rotating around the x-axis. And this time I'm using the shell. When I use the shell, it means I have to take slices which are parallel to the axis of rotation. So this is my axis of rotation. So my shell has to be horizontal. So that's my, and this is my yi. Y is my variable. So this is what we're going to rotate. And we get a cylindrical shell. It should be a little bit more. Okay. So that's where the center of rotation is. That's really where my center of rotation is. In this situation, so this is the thickness of my shell. So in this situation, y is the variable. So everything has to be in terms of y. Everything in terms of y. Step number 1, we have to ask ourselves which interval I need to split into pieces. I am on the y-axis. We have to split the interval from here to here. Now, what's the point here? This is where x is 0. It means this is 4. Okay, so we have our limit. Now, we have to find every piece for the shell. A shell is characterized by the radius, the height of the shell, and the thickness. So in this case, the thickness is the delta y, the radius, and the height. All right, so let me get back to you very quickly. What's the height in this problem? Sorry, what's the radius in this problem? You guys have to take the quiz, so you have to wake up. What's the radius in this problem?
yi.
Yi. It's from here, from your rectangle till your axis of rotation. This is my yi. What is the height in this problem? Because on the picture, that's the height. It's the length of the rectangle. So give me the height quickly.
4 minus y.
Repeat. I think you're right.
Minus y.
Yeah, we have to solve for x. X is 4 minus y. We need a horizontal distance. It means this is yi. I need the x that correspond to this yi because this point is on this line. So from here to here, it's the x that correspond to that, which is 4 minus yi. So that's the height. So it's not hard either way, actually. It's really easy both ways. So volume of a typical shell is almost equal to pi times the radius times the height times the thickness. So it's basically 2 pi r. 2 pi r is nothing more than the length of the circle times the height times a little bit of thickness right there. That's the volume. So finally, the total volume is the integral of 2 pi y 4 minus y dy. And always we have to worry about the limit. So we go back, ask ourselves which interval we need to divide into pieces to cover the region with a rectangle. Very quickly, what are the limit of integration? What are the limit? What's the lower limit and what's the upper limit? It's so quiet.
0
to
and 2.
2, absolutely, 2 to 4. So that's the total setup. Now to evaluate, again, we have one way here is to distribute. And then the rest is easy. I will have 4y minus y squared dy. And the rest is simple. Okay.
Professor,
Yes.
could we say 2 to 4? Could we say 4 to 2? If we change
We
this
usually
for
from the bottom to the top. It doesn't really matter if you understand what you're doing. But we usually we say from 2 to 4.
let me see. Thank you.
Okay, so the bottom is 2, the top is 4. That's crucial, the upper and the lower. Okay. All right. So today we're going to move on to section 6.5. Length of a curve. Or sometimes we call this arc length. So length of a curve or arc length. So what are we talking about? So it means what we're interested in is the following. Let us say you have a curve. Something that's curving. Okay. And the question is to find the length of this curve. What does it mean, the length of the curve? It means if you take the thing that's curving and you actually stretch it and you measure it, what's the length of it? Okay, that's really what we have to find out. All right, before we start with something complicated like a length of a curve, let me remind you length of arc segment, of line segment. So the question is, what's the length? That's really my question. Okay. Let me start with a simple question, length of line segment. What do I mean by that? Suppose you have a line segment. So this is it. A line segment, something like that. That's a line segment. Something that connect 2 points. Okay. So, and let us say this is a point A and this is a point B. So a very simple question. What's this length of the line AB? What's the length of this line? or if you want, which is nothing more than the distance between those 2 points. So the length of AB is nothing more than the distance between the two AB. Okay, what's the distance between them? So since I am in a plane, I'm going to give them coordinate. I'm going to call this point has for coordinate x0, y0 if you want. And this has for coordinate x1, y1. Okay, who can give me the distance between them in terms of their coordinates? Anybody can figure it out? I'll help you. By drawing this rectangle. It's not the slope, it's the length. It means how much it's measured from here to here. Right, okay. All right, now we're getting that. Pythagorean, exactly. So let's do Pythagorean. What's the distance from here to here? What's the vertical distance? Is the y value here minus the y value here. So this is y1 minus y0. What's the horizontal distance? Is the x value here minus the x value here. So the right value minus the left value. So if I call this distance d, just to make things easier for us, Pythagorean tells me that d squared is x1, the change in x squared, plus y1 minus y0 squared. Okay, so this is nothing more than the Pythagorean. So the distance d is going to be the square root of x1 minus x0 squared plus y1 minus y0 squared. So if I have a line segment, something as simple as that, and I want to find the length of it, which is nothing more than the distance between them, I can use this formula. So the question is, I'm going to go back to a curve. I'm going to find the length of a curve. Okay, so let us put the correct setup. How can those curves be generated? It means in math, where do we get the curves from? We're going to look at the curve, which are the graph of functions. So our curve will be nothing more than the graph of functions between 2 points. So in this section, okay, we will consider curves that are graph, means the actual graph of a function between 2 points. Let me call those points A, f of A, and B, f of B. So what am I talking about? I'm talking about the following. The curve I'm going to be looking at are that's my point. That's the graph of a function. That's the graph of a function here. So that's my graph, y equal f of x. And this is my point, A. And this is the point, B. So this point right here, that's A f of A. And the point here is B f of B. Okay. And the question is how I'm going to find the length of this curve. What am I supposed to do? It's really complicated. This is curving. So how I'm going to find the curve? So the question is, the goal, find the length. Okay. What are we going to do?
You could take fairly small segments and add them all.
Exactly. This is a very complicated curve. We have no idea how to find its length. So we're going to approximate it by the length of something we know. And the only thing we know how to find its length is a line segment. That's the only thing we know. So we're going to chop this into pieces, covering it with tiny, tiny line segment, find the length of each line segment, and then add up the whole length. So that's really our idea these days, is that we don't know what to do something, we chop it into pieces that we know, and then we find the volume, the area of every piece, the length of every piece, and we add them. So let's do the chopping. Now let's see how we're going to chop those pieces. I'm going to chop them here. And we will chop them like this. So I'm going to divide this into pieces. Now, of course, I don't do a lot of them because it's tedious. So I'm going to call this X1, X2, X3, what we're going to call the general piece, the representative piece, the typical piece, Xn. And these are how the pieces are going to be. This is point X1. My first line segment is from here to here. That's my first line segment. This is my X2, my second line segment. As you see, so that's the segment that we're going to subdivide. This is X3. This is the segment. That's how we are going to cover the curve. And we keep going. We keep going. So xi plus 1. This is my line segment here. And basically, that's my idea. My idea is going to keep line segment, line segment, line segment, line segment, line segment. That's what we are doing. So instead of finding the length of the curve that I have no idea, I'm going to cover it with line segment. And the smaller those lines, the closer we are to the curve. So now what I'm going to do is I'm going to find the length of this and the length and the length and add them. So let me give them name. I'm going to call this P0. I'm going to call this P1. This I meant the point. I'm going to call this point P3. So this point here, I'm going to call it Pi. This point here, Pi plus 1. And this point here, Pi. And I'm going to find the length of everyone. So as usual, we concentrate on a typical one and we find its length. So here we going to find length of the line segment, Pi plus 1. Okay, all right, let's see how to do that. So I'll start a new page just to make the picture clearer. So this is really what I want. That's Pi plus 1, and that's the line. Now, to do that, before I start my new page, we need the coordinate of Pi, and we need the coordinate of Pi plus 1. Quickly, what's the coordinate of Pi? This is xi here. And this is the value of the function at xi. Pi plus 1, xi plus 1, the value of the function at xi plus 1. And that's the line that I need to find its length, this line right there. So let me draw it here for us. So this is Pi, this is Pi plus 1. So this is xi, f of xi, and this is xi plus 1, f of xi plus 1. And this is my point Pi plus 1. And really, I need to find the length of that. Okay, so let us come up with the formula and then we add them. Okay, the lengths of Pi plus 1. The line segment Pi plus 1 is equal to the square root of the change from here to here. Let me call it delta 1 because I don't feel like writing f of xi plus 1 minus f of xi. Let me call it delta 1 because the change in 1 squared. Plus, I want to call this the delta x squared. Okay, so that's really what the length is. All right. Now I'm going to do a little bit of algebra, and this is equal to what? I'm going to factor out the delta x. I factor it out. And if I factor it out, so I'm going to do a little bit of tricks to come up with the formula. This will gonna give me a 1 from here. And this will give me the delta y square, since I factored out this one over the delta x square. I know it's a little bit weird, but very soon the formula will be very clear. All right, so it's gonna give me what? So, all right, now equal to this delta x square, I can take it out. So I'm gonna put it here. So I'm gonna factor this out, the square root, and then I will be left with 1 plus delta y over delta x square. All right? Now, I'm gonna focus on this. What's delta y over delta x square? What's delta y over delta x? It's nothing more than the change, whatever, over xi minus xi plus. That's really the delta y over delta x. So in this picture here, back to you, delta y over delta x. And now I'm going to ask you a question. When delta x is very small, when delta x is small, the delta y over delta x is basically what? Why is delta y over delta x? Did you see how I factored out delta x square? No, I factored out delta x square here. What did I get? 1 plus delta y squared over delta x. If you multiply back delta x squared, you multiply this time that, you get the delta y squared. Alexis, are you with me? Alexis. Okay, so I just factored it out just because we want to come to the formula. I mean, I know that this is, and then this delta x squared, I just cut it out, factored it out because square, I factored delta x, and I'm left with this. Now I want to analyze this piece right there. I want you to think a little bit. What's delta y over delta x? When delta x become very small and it's not infinity. Quickly. So remember, if you have a curve, like we had, this is xi and this is xi plus 1. And I take the delta y over delta x. And then I'm going to let delta x become very small. Does this remind you anything? (163). The heart of 163. The most important idea of 163. That's the derivative. Exactly. The change of y over change in x. The change in y over change in x. When the change in x become very small, this is nothing more than the derivative at xi. Okay, so this delta y over delta x, if you guys remember, what's the derivative here? You take a point close and you start taking the slope, which is the delta y over delta x. And delta x becomes small, you're taking smaller and smaller slope till you are actually getting close to the tangent line. All right, so now this is going to tell me that this is almost equal to the square root of 1 plus the derivative at xi squared times delta x. It's very interesting where this formula comes from. So the length of the curve is going to be almost the sum of those quantities. Times delta x. And that's where my Riemann sum is going to come up. So the length now, we're going to come the formula for the length. So the length is going to be equal to the integral from A to B of the square root of 1 plus f prime of x square dx. Okay, so length of the curve